Hello AP Chemistry and welcome to the very last section for Chapter 20, electrolytic cells. So here is where we take what we've been talking about and we flip it all in the other direction, right? We have talked all chapter about galvanic cells, which have a positive E0 value, right? And happen on their own without any outside intervention, right? Now we're talking about electrolytic cells where the key difference is going to be that we will need a voltage source, right? Every electrolytic cell has a power source, right? So here, this has to be something that supplies power versus something that requires power or measures power, okay? But otherwise, right, the setup is exactly the same, right? We have electrodes, right? We have an anode and we have a cathode. Oxidation still happens at the anode. Electrons still flow from the anode to the cathode, right? And then we still have to maintain electrical neutrality. We still have to maintain electrical neutrality down here, right? Again, so flow of electrons down here, electrical neutrality. And we still have to be thoughtful about what is able to be oxidized and what is able to be reduced. Just now, we're going to think about it as our overall E0 value is going to be 0 or negative, right? And we're looking for, well, we'll get there in a minute. Okay. The only thing to take note of that I guess is up here for our power source, right? We do need to be mindful that electrons, again, coming from the anode, right, are going to flow to the positive end of my power source, right? Which makes sense, right? Because if we think about it, the electrons are negative and they're going to flow to the positive, right? And that's what happens in a galvanic cell. They flow from the negative end to the positive end. Just here now they're flowing up to the positive end of my battery, right? So an artificial positive, right? And the battery is then going to pump out electrons, right, from its negative end to do the reduction. Yes, so that's how that is sort of powering our process. Okay. So here we have molten NaCl, right, which note is different than aqueous NaCl. When we say molten NaCl, what we mean is we took salt, table salt, and we melted it, right? We heated it so hot that it melted, which means that my only species in solution are going to be sodium ions, not solution. My only species present are sodium ions and chloride ions. So in terms of considering what reactions are going to occur, and this figure doesn't have it listed, but these are inert electrodes, right? So then what's going to happen is we're going to have chloride being oxidized, and we're going to have sodium being reduced, and that's going to be my overall set of reactions. And if we go back to our table of standard reduction potentials, right, if we pick out chlorine, right, the oxidation of chloride ions is actually negative 1.36, right? So negative 1.36. Sodium down here, reduction of sodium is negative 2.71. Right? So indeed, our overall voltage is decidedly negative, which means that our power source has to be able to provide at least that much voltage, if not more. Yes, does that make sense? So if we look here, now we have a different kind of electrolytic cell, where if we look up here, again, we have a voltage source, which gives us big clue that this is an electrolytic cell, right? And again, we have the same basic principle, right? Where if we look at here, our power source, if this is our positive end, right, that means this must be our anode, right? And this must be our cathode, right? And here, this is purposely designed so that way we will plate my object with nickel, okay? Now, your book goes through how to figure out what reactions are occurring, right? Where first, and make sure you pay attention because this is basically what all your questions are, right? And we did the same basic thing when we talked about our galvanic cells, where first we need to figure out what's present, right, and what is possible in terms of happening, right? So if you think about all of our species, right, we know we have some nickel ions, and we know we have some water. Oh, and your book goes on to say that this is a nickel sulfate solution, right? But sulfate is pretty much never going to be a participant in anything, right? So we know that these are really our two options present to do anything, right? Here, this is made of steel, so nickel solid is, oh, sorry, we have some nickel solid. So here we have all of those options, right? We have nickel solid, we have nickel ions, and we have water, right? This is my anode, meaning oxidation has to occur here, which rules out nickel ions, right? Because nickel cannot be higher than +2, right? Which leaves us with nickel solid and water, right? So in order to figure out which is going to oxidize, we're going to use the one that is most likely to occur, right? So if we go back a couple pages, right, nickel versus water. So nickel plus 2 is right here in terms of reactions, right? And we were looking at anode to oxidation of water, which means that we'd be looking on the product side, right? So we would be looking over here to find water as a product since we're trying to read it in the backwards direction, right? So we're looking for the for water, and here is our water. So in terms of oxidation processes, right, so we can have solid nickel being oxidized, or we can have water being oxidized. This is going to have a value of negative 1.23. This is going to have a value of plus 0.28. So in terms of which of those is easier or more likely to happen, it's going to be this one. Yes? Does that make sense? So if we go forward 2 slides, that is indeed what happens. Yes? All right. Over here for our reduction reaction, right? So we know reduction has to happen here, which means that if we think about our species, again, we have some nickel plus 2, right? And we have some water. So let's go back and look at what those are, right? So nickel and water. So again, this is still nickel. Let's circle in a different color, right? So this is still my nickel. And now we're looking for the reduction of water, which means we're going to read it forwards. And here is our reduction of water. Turns out that this, at being negative 0.28, is more likely than this one, right? Now, that's not to say this one cannot happen, right? If our power source has a high enough voltage, then we can get both of those things to happen, right? But obviously, we would try to design it and use a low power voltage, right? So that way only this one happens, okay? Which is why, going back over here, right, we're going to get the reduction of nickel here. So we get solid nickel on this electrode, right? We get the production of nickel ions over here, right? Now the overall E naught value for the cell is what? Right, clearly 0. E naught equals 0. And we know that because it's the same thing happening on both sides. So x and negative x means the overall thing is going to be 0. Which means that, like I was saying before, we don't need a lot of voltage to make this process happen, okay? Note that sometimes you want them both to be negative, right? That's our natural inclination, but that doesn't have to be true, right? Like here, right, when we looked over here, this is actually a spontaneous process, but we're looking at the overall cell voltage, right? Needs to be unfavorable, right? Does that make sense? All right, so in terms of the kind of math you need to be able to do with this, right, outside of obviously using the Nernst equation, one of the things we talked about, I don't know if we talked about it earlier, amps is equal to coulombs per second, right? So when a word problem gives you some information like a current of 10 amps was run, right? What that translates to is 10 coulombs per 1 second, right? And let's say it tells you that the cell runs for 60 seconds, right? Then you understand that that is a set of conversions you can do, right? So for example, I can take my 60 seconds, and I know that if I'm running 10 coulombs for every 1 second, I've now converted to coulombs, right? And I always know Faraday's constant, which is 96,485 coulombs for every 1 mole of electrons. And now that sets us up to do some reaction stoichiometry, right? Wherein we've taken some a flow of electrons and how long those electrons were flowing, right? And my Faraday's constant. And then we can tie that to reaction stoichiometry for how many electrons per mole of actual substance, right? And figure out how much stuff is plated, right? Or how much solid comes out, right? Or if I have a desired amount of solid, I can figure out how long I need to run a current backwards and forwards. Yeah, makes sense? All right. Sorry. I do believe that is it. All right. That ends chapter 20, last chapter of the year. Thank you for listening. Be good, and I'll see you soon. Bye.